Hey everyone, welcome to my next video. Today I'm going to talk about pathfinding, and specifically about the A-star algorithm, which is really popular in games. What I'll do today is go over the core of the algorithm, going through some explanations and providing pseudocode, and then walking through some examples, step by step, so that you can see and understand how it works really thoroughly. I'll also have full source code in JavaScript available online at the GitHub address in the description, so you can check that out if you're interested. In the future, I'll have some more advanced tutorials that walk through some of the ways to make the algorithm more efficient, but today we'll keep it simple and we'll focus on getting a grip on the basics. So, to begin, what is the A-star algorithm? At its core, it's a graph traversal algorithm, in very much the same way that depth-first search or breadth-first search are graph traversal algorithms. In fact, you can use depth-first search or breadth-first search to do pathfinding. It's just incredibly inefficient, but it works. The key difference between A-star and depth-first search or breadth-first search is in the heuristic, which attempts to steer the algorithm towards the goal, instead of blindly iterating the entire graph until the goal is found. In games, especially games with dynamic environments where things can be blocked 1 minute and open the next, you blow up a door or something like that, A-star is commonly used to find paths for units from point A to point B. So, before we look at the pseudocode, here are some quick definitions, things that A-star relies heavily on, and you should have a grip on them. You'll see and hear references to both an F-score and a G-score throughout, in both the pseudocode and in the examples we'll walk through, so it's really important to at least get these two concepts down. G-score is really straightforward. At any point on the map between the start and the end, when you want to calculate the G-score, it refers to the distance or kind of the cost of moving all the way from the start to the current point. You could imagine if you were a person in a maze, for example, this would be how many steps you took to get to where you are. It's not the bird's eye view distance, it's literally the walking distance, so including going around corners, upstairs, things like that. F-score is a little more complex. At any point on the map, you know how long it took to get there, but you're not sure how far away it is from the goal. So the F-score is the sum of the cost to get to that point, plus a guess at how far away you are from the end. So going back to our maze example, if you're at some random spot in the maze, you know how many steps it took to get there. And the estimated distance to the goal could just be the distance from that spot to the goal, ignoring the wall. So if you were to draw the map from above, it would just be a line straight from that point to the goal. Here's the pseudocode. Let's take a quick look. What A-star is doing, it keeps what's called an open list, which is sorted by F-score. At every step in the algorithm, it takes the node with the lowest F-score, checks out all the nodes connected to that one, and calculates the G-score for each of them. If that new G-score is lower than the current G-score for that node, it adds it to the open list, if it wasn't already in the open list. Here's a picture that hopefully will clear things up. So you've got this guy standing in the maze, trying to find his way through. He's kind of walked down and around the first wall, so his G-score could just be how far he walked to get to that point he's at now. So I kind of drew his footprints in blue there, and you can follow them. And if you were looking from above, say from a bird's eye view, you could see roughly how far this little guy is from the end of the maze. Again, ignoring the walls. In this picture, I just called that the H distance. In code, it's often referred to as the heuristic function. Now, the F-score, which is really so important in making A-star work, is just the sum of these. It's G plus H. So it's the G-score, or how far you've walked to get to the spot in the maze, plus the H-score, or the guess as to how far you are away from the end. So if this still sounds a little complicated, we'll walk through some examples step by step. In the first example, we'll start at the top left, and you can see that the X is just a few squares away. When we start, we'll calculate the F and G scores. Since we started at this point, the g-score, or how long it took to get here, is 0, since it didn't take any time to get here. Then we started here. You can also see that we're about 4 squares away from the x. So it stands that the heuristic would guess that it's about 4 away. And so the f-score, which is g plus h, is 4, since it's 0 plus 4. Now, if you remember the pseudocode, we choose the open node with the lowest f-score, which in this case is the top left, since it's the only one. And then we expand out every node that connects to that one. In this case, since we're only allowing left, right, and up, down walking, we expand out the nodes below and to the right. You can see that the g-score for each of these nodes is 1, since it took 1 step to get there. The f-score for the one below is a little higher, because it's actually a little bit further away from the goal. So once you count the distance from that to the goal, and you add 1, you end up with a higher f-score. The f-score for the one on the right is still 4, because g is 1, but now you're only 3 squares away. So h would be 3, and 1 plus 3 is 4. So let's do another round of updates, and now we'll check out some more neighbors. And you can see that the g-score for all the new neighbors is 2, since it takes 2 steps to get to each of these new ones. And the f-score for the one on the right is still 4, since now you're only 2 away from the goal, and the g-score to get there was 2. Updating again, we expand only one neighbor this time because it's blocked underneath. And you can see that the f and g scores updated similarly to how they did before. And finally, in this last step, we hit the goal. In this case, the g-score is 4 because it took 4 squares of movement to get there. But since we're at the goal, the distance to the goal is 0, and so the f-score is 4 because that's g plus h, which is 4 plus 0. Let's move on to a slightly more complicated example. This one will lead us a bit away from the goal at first before eventually moving back towards it. We can see in the first step the 2 neighbors are expanded, and the green one is the one with the lowest f-score, so it's chosen. Now we know that we need to go down and around the wall before hitting the goal, since you can see the whole map. But A* can't see the entire map like this. In the next step, you can see that the next node chosen was the one directly under the start, since among the open nodes, it had the lowest f-score. After that bottom one is expanded, it chooses to go to the one on the right, and 2 more nodes are expanded, below and to the right. This time A* decides to try for that little crevice in the wall, since it's potentially the best chance of getting to the goal. Now, we can see that it's not. We can see that this is a dead end, but like I said, A* doesn't see the entire map, it only sees one node at a time and whatever it's seen in the past. So it's back to expanding, and we can see as this moves along, all it's doing over and over is checking out some new nodes, assigning G and F scores to each one, and then choosing to explore the one with the lowest F score. Eventually, it checks out all the nodes on the left side of the map, and now we can see it starting to creep around the bottom of the wall. As it does that, the f-score is starting to stabilize, and you can see that it's starting to make a beeline for the goal. Notice how it's considering, but not exploring the nodes on the right side. You can see that the f-score leading to the goal is now 10, and those f-scores on the right are 11.16 and 11.24 at this point. So they're not going to be explored by the A* algorithm unless it can't get to the goal with the nodes it's exploring right now. This is all working on these small toy examples. Let's throw some harder maps at this thing. I coded up a really quick maze generator. Let's see how the A* implementation handles some much bigger maps. Okay, so it looks like our A-star implementation was doing fine, but we broke the maze generator. It looks like I have to rewrite this thing as an iterative algorithm. Anyway, hopefully this is all clear. Like I said, source code is available on GitHub. Next time we'll do a deep dive through the actual code and implementation, and we'll talk about some optimization opportunities and trade-offs as well.